Welcome back to our deep dive into computer science and software engineering.
Um,
Today, we're going to be tackling finite choice logic programming.
okay.
It's a pretty fascinating area, and we're going to break it down for you using a combination of research papers and some practical examples.
Yeah.
We'll explore its history, how it actually works, and how it kind of stacks up against some other approaches like answer set programming.
It's a really clever way to represent and solve problems
Yeah,
that have multiple solutions,
right.
which is something that's challenged computer scientists for a long time.
Absolutely.
Yeah.
Okay, so before we kind of get into the specifics of finite choice logic programming,
Sure.
let's quickly recap some logic programming basics.
Yeah.
I know we've touched on this before,
Uh-huh.
but a quick refresher never hurts, right?
Absolutely. A good place to start is with horn clauses.
Right.
They're kind of the foundation of traditional logic programming.
Right.
You can think of them as a way to express logical implications.
Right, like if this, then that kind of statements.
Exactly. And they're written in a very specific way.
Okay.
You have a head, which is what you're trying to prove true,
Right.
and a body, which are the conditions that need to be met for the head to be true.
Gotcha.
It kind of looks something like this, like A, B1, Bn.
Okay.
It basically means A is true, if B1 and B2, and so on are all true.
So if we use the classic example, if it's raining and you're outside, then you'll get wet.
Right.
Raining and being outside would be our B1 and B2 are conditions.
Yeah.
And getting wet would be A, our outcome.
Perfect.
Yeah.
Now, to apply this to logic programming, we use things called predicates.
Okay.
These are basically like verbs. They describe relationships.
Gotcha.
So, for example, father-child is a predicate,
Okay.
and Charles and William would be the specific people it relates to.
Sure.
You use terms,
Yeah.
which can be constants like Charles's,
Okay.
or variables like X to represent specific individuals.
Okay, so father, child, Charles, William
Mm-hmm.
would mean
Exactly.
Charles is the father of William. That's actually a pretty elegant way to model real-world relationships.
It is. But here's where traditional logic programming sometimes hits a snag.
Okay.
It can be a little tricky to express problems that have choices
Okay.
or multiple possible solutions.
And that is where finite choice logic programming comes in, right?
Exactly.
It introduces this idea of choice
Yeah.
as a core concept.
Yeah.
Instead of saying what can't be true,
Yeah.
it focuses on the different options that could be true.
Exactly. And it's a much more intuitive way to model scenarios where there isn't just one right answer.
Right.
The paper, Finite Choice Logic Programming, Theory, Implementation, and Benchmarks, breaks this down beautifully.
Yeah.
In addition to facts, which we just talked about,
Yeah.
you have these things called functional dependencies
Okay.
and two types of rules, open and closed.
Okay, let's unpack that. What are functional dependencies?
Okay, so they make sure each attribute has at most one value.
Okay.
So imagine you're designing a level in a game. Sure. Each region on your map
Yeah.
can only have one terrain type. It can be a mountain, a forest, or an ocean, but not all three at the same time.
That makes sense. And how about open and closed rules? What do those do?
So open rules
Yeah?
allow for a range of possible values.
Okay.
So a rule might say the terrain of this region could be anything.
Gotcha.
A closed rule, on the other hand, specifies a fixed set of choices.
Okay.
So it might say the terrain of this region must be either forest or ocean, but not a mountain.
I see. So you could use open rules to initially define the possibilities for each region.
Yeah.
And then use closed rules to introduce constraints based on your game's logic.
Exactly.
Like oceans can't be next to mountains or something like that.
You got it.
Yeah.
It's a powerful way to model complex systems with lots of interconnected parts.
Right.
But how does the program actually figure out
Yeah.
which combinations of choices are valid?
Right.
The paper mentions something called fact set semantics.
Yeah, I was curious about that too. What's that all about?
It's basically a way to understand how finite choice logic programs are evaluated.
Okay.
It's a step-by-step process of building up a solution by adding facts to a database.
So you start with a blank slate
Right.
and apply rules to add facts until you can't add any more.
Exactly. And this process of applying rules until you can't apply anymore is called saturation.
Okay.
But here's the key.
Yeah.
There might be multiple paths to reach saturation,
Okay.
each leading to a different valid solution.
Wait, I'm a little confused. If the program is applying rules, how does it choose which path to take? Does it just randomly pick rules to apply?
That's a great question.
Yeah.
It doesn't pick randomly.
Okay.
It systematically explores all possible paths,
Okay.
branching out whenever there's a choice to be made.
Okay.
So let's say you have a program with two attributes, P and Q.
Okay.
One rule says P can be either true or false.
Okay.
So the program creates two branches, one where P is true and one where P is false.
Okay, so it's like the program is making a copy of itself and exploring both possibilities simultaneously.
Precisely.
Okay.
Now imagine another rule says, if P is false, then Q must be true.
Okay.
In the branch where P is false, this rule would kick in and add the fact Q is true
Correct.
to that branch's database.
So now we have one branch where P is true and we don't know anything about Q yet.
Right.
And another branch where P is false and Q is true.
Exactly. And the program keeps applying rules to both branches.
Right.
Until it can't apply any more rules.
Right.
That's when it reaches saturation.
Okay.
And each of those saturated branches represents a complete solution.
Okay, so it's like the program is systematically exploring a maze of possibilities, finding all the hidden exits. That's a really neat way to find all valid solutions, not just one.
It is. And while this fact set semantics might seem simple,
Yeah.
it's actually a powerful foundation for understanding how finite choice logic programs generate their solutions. Yeah.
This is all very interesting.
Yeah.
Now, the paper also briefly mentions constraint databases
Right.
and fixed point semantics.
Yeah.
I know you said we're trying to keep this high level,
Sure.
but can you at least give us a quick idea of what those are about?
Sure. Think of them as providing a more formal mathematical foundation
Okay.
for what we've been talking about.
Right.
They give us a rigorous way to define the meaning of these programs and
Okay.
ensure that everything works as expected.
Okay, that makes sense. So we've got the basics of logic programming
Right.
and how finite choice logic programming expands on that.
Yeah.
We've also touched on how these programs are evaluated.
Huh?
Now, I'm really curious to see some real-world examples of how this all works in practice.
Yeah.
Ready to dive into those.
Absolutely. Absolutely. Let's look at some examples.
Okay.
One that really illustrates the power of finite choice logic programming is the spanning tree problem.
Okay. Spanning trees. I remember those from my algorithms class, but it's been a while. Could you remind me what they are?
Of course.
Yeah.
A spanning tree of a graph is basically a minimal set of connections that allows you to reach every node in the graph
Okay.
without creating any cycles.
Okay.
Imagine you have a network of cities connected by roads.
Mm-hmm.
A spanning tree would be like a map that shows you the most efficient way to travel
Yeah.
between any two cities without going in loops.
Right. It's like the bare minimum connections you need
Exactly.
to keep everything connected.
Yeah.
So what's so special about spanning trees and finite choice logic programming?
Well, the interesting thing is
Yeah.
that a graph can have multiple spanning trees,
Okay.
and finite choice logic programming can help us find all of them.
Hold on. Multiple spanning trees. How is that possible? Wouldn't there just be one best way to connect everything?
Not necessarily.
Okay.
Think about it this way. If you have multiple roads connecting the same two cities,
Right.
you have a choice of which road to include in your spanning tree. And depending on which roads you choose,
Okay.
you can end up with different spanning trees
Okay.
that all satisfy the basic requirement of connecting all the cities without any loops.
Okay. I see. So how does finite choice logic programming actually find all these different spanning trees?
It uses open and closed rules
Okay.
to explore different ways to connect the nodes in the graph.
Uh-huh.
It starts by picking an arbitrary node as the root of the tree.
Okay.
Then it uses rules to add edges one by one,
Okay.
making sure that each new edge connects a node that's already in the tree to one that isn't,
Right.
and that we don't create any cycles.
So it's like building the tree branch by branch,
Exactly.
making sure each new branch connects to the existing tree but doesn't create a loop,
Right.
and each time it adds a branch.
Yeah.
It's essentially making a choice about which edge to use.
Exactly. And each time it reaches a point where it's connected all the nodes without any cycles,
Yeah.
it's found a valid spanning tree. And by exploring all possible choices,
Right.
it can find all the different spanning trees for that graph.
That's really clever. Now, the paper compares this approach to something called Datalog.
Right.
I'm not super familiar with that.
Sure.
Can you tell me a bit more about it
Yeah.
and how it compares to finite choice logic programming?
So Datalog is another type of logic programming language,
Okay.
similar to Prolog.
Okay.
It's often used for querying databases
Okay.
and reasoning about relationships between data.
Uh-huh.
But when it comes to problems like finding all spanning trees,
Yeah.
Datalog can get a bit tricky.
Okay.
It often relies on recursive rules,
Okay.
which can be hard to manage when you have multiple solutions.
So it's like trying to describe the steps to build one specific spanning tree
Right.
instead of defining the rules that a-wise valid spanning tree must follow.
Exactly. Finite choice logic programming is more declarative.
Okay.
You're focusing on what the solution should look like,
Right.
not on the specific steps to get there. This makes it much more intuitive and flexible for dealing with problems where there are many possible solutions.
Okay, I'm starting to see the advantages here.
Yeah.
The paper also talks about using finite choice logic programming to find connected components of a graph.
Yes.
Can you explain what that means and give me an example?
Of course.
Yeah.
Think of a social network like Facebook.
Okay.
You have people, and those people are connected by friendships.
Right.
A connected component is a group of people where everyone is either directly or indirectly friends with everyone else in that group.
Right. So it's like identifying all the distinct friend circles within a larger network.
Exactly.
Each friend circle would be a connected component.
Precisely.
Uh,
Finite choice logic programming can do this really elegantly.
Okay.
It assigns a unique representative to each connected component.
Okay.
The rules would ensure that any two people connected by a friendship have the same representative,
All right.
and that each person only has one representative.
So it's like labeling each friend circle with a unique color. That makes it easy to visualize all the different groups in the network.
Exactly. And again, the program can find all possible ways
Okay.
to assign these representatives,
Right.
which means it can find all the valid ways to divide the network into connected components.
Okay. This is really driving home the point about multiple solutions. Now, this next one is really intriguing to me.
Okay.
The paper mentions that finite choice logic programming can handle infinite domains.
Right.
That sounds almost impossible. Can you explain what that means and how it works?
Sure. In traditional logic programming, you're usually working with finite sets of facts.
Right.
But finite choice logic programming can actually deal with situations where the set of possible values is infinite.
Wait, infinite programs. My brain is already starting to melt. But seriously, how do you prevent the program from running forever if it has to consider an infinite number of possibilities?
It's all about how the program is designed.
Okay.
The interplay between open and closed rules allows it to reason about infinite sets, while still ensuring that it can find solutions in a finite number of steps.
Okay.
Let's say you have a predicate called stop n,
Okay.
where n could be any natural number.
Okay.
Open rules would allow for any possible value of n,
Okay.
while closed rules would add constraints based on the specific problem you're trying to solve.
So even though the set of possible values for n is infinite,
Right.
the program uses the closed rules to narrow down the possibilities
Yeah.
to a manageable set that it can actually work with.
Exactly.
Yeah.
It's a very elegant way to combine the expressiveness of dealing with infinite sets
Yeah.
with the practicality of finding solutions in a finite amount of time.
This is really fascinating. Now, we've talked a bit about answer set programming,
Right.
but we haven't really dug into what it is
Sure.
and how it compares to finite choice logic programming.
Yeah,
Could we spend a few minutes on that?
absolutely. Answer set programming, or ASP, is another declarative programming paradigm
Okay.
that's become popular for solving complex combinatorial problems. Okay, it's all about finding stable models,
Okay.
sets of facts that satisfy all the rules of the program without any contradictions.
Okay, so it's about finding consistent sets of truths.
Yes.
How does it compare to finite choice logic programming?
One key difference is that ASP uses negation
Okay.
as a core concept.
Okay.
You use not in your rules to express things that must not be true.
Right.
Finite choice logic programming, on the other hand, achieves the same expressiveness without using negation directly.
So it's like saying, instead of listing all the things you can't have on a pizza,
Right.
you list all the possible toppings and let the customer choose. You get the same result, but it's a more positive way of thinking about it.
That's a great analogy.
Yeah.
And while both paradigms can solve similar problems,
Yeah.
there can be performance differences.
Okay.
Finite choice logic programming, especially with implementations like the DUSA language, can be more efficient in certain scenarios
Okay.
because it avoids the complexities that come with negation.
Okay, so finite choice logic programming might offer a performance advantage in some cases. But how do you actually write and run these programs? Is there a specific language or tool that's used?
That's where the DUSA language comes in. It's a concrete implementation of finite choice logic programming.
So if finite choice logic programming is the blueprint, DUSA is the building you make from that blueprint.
Exactly. DUSA brings those theoretical concepts we've been discussing into the realm of actual code.
Okay.
It gives you the syntax for writing those rules,
Right.
a system for evaluating the programs, and a way to interact with the solutions.
That's amazing. So what are some of the things that make DUSA stand out?
One of the coolest things about DUSA is its ability to handle those potentially infinite programs we talked about earlier?
Right.
Remember how finite choice logic programming can work with infinite domains?
Yeah,
DUSA brings that capability to life.
that's powerful. It means you're not limited to problems with just a finite set of possibilities. It opens up a whole new world of potential applications.
It really does. And DUSA was also designed to be easily integrated with other systems.
Okay.
Think about it. You can embed this right into a game engine
Right.
or any other software.
That makes a lot of sense, especially since it has roots in procedural content generation for games.
Right.
It needs to work smoothly with existing tools.
Right. Another key feature of DUSA is its emphasis on randomness and predictable performance.
Okay.
It's designed to give you a way to explore all those possible solutions
Yeah.
in a really controlled and efficient manner.
So not only can it find the answers,
Right.
but it also lets you fine-tune the search process itself.
Precisely. And the paper actually compares DUSA to other logic programming systems,
Okay.
like Klingo and Alpha.
Okay.
It turns out DUSA performs quite well, especially in situations where its unique approach to program evaluation shines.
Okay. That's really impressive. We've covered a lot of ground today, from the fundamentals of logic programming to the nuances of finite choice logic programming and the DUSA language. It's been a fascinating journey. What are some of the key takeaways you hope our listener walks away with today?
I hope they understand that finite choice logic programming offers a really powerful and intuitive way to tackle problems with multiple solutions. It's more about defining what a valid solution looks like rather than outlining specific steps to find it.
And it does this by using the concept of choice as a fundamental building block,
Exactly.
which allows it to explore a wide range of possibilities without getting bogged down in negation like some other approaches.
Exactly. And with implementations like DUSA, we're seeing the practical potential of this approach really starting to come to life.
This has been a really insightful deep dive. Thank you for walking us through all of this. Any final thoughts for our listener before we wrap up?
Absolutely. Think about the problems you face in your own work or projects. Could finite choice logic programming be a useful tool in your toolkit? The possibilities are vast, from game design to configuration management to modeling complex systems and even exploring the nature of human reasoning. There's a lot of potential here for creative applications.
That's a great point. It's a reminder that sometimes the most elegant solutions come from thinking about problems in a different way. Well, that brings us to the end of this deep dive on finite choice logic programming. We hope you've enjoyed this exploration and that it sparked your curiosity to learn more. Until next time.